Welcome to This Explainer. Okay, let's dive into this, because today we're exploring something incredibly cool that sits right at the intersection of ancient history and modern computer science. We're going to see how just a handful of lines of Python code can literally act as a digital time machine. You know, when we think of historians or geologists, we usually picture folks out in the field, right? With brushes, pickaxes, getting their hands dirty. But today, our primary excavation tool is just code. We're going to look exactly at how a computer program can peel back the layers of time to uncover the hidden age of ancient physical materials.
So picture this for a second. Imagine you're holding this really ancient piece of quartz right in the palm of your hand. It's rough, it's cold to the touch, and honestly, it looks totally silent, just a dead rock, right? But it's actually holding on to centuries, maybe even millennia of secrets. And that brings up a massive question for us as digital detectives. How do we measure the invisible past? I mean, when the people are long gone and there are absolutely no written records left, how does the Earth itself keep track of time? Figuring this stuff out is what actually lets us unlock ancient climate shifts and map early human migration patterns. And the answer? It's all about microscopic clues hitting deep within the structure of that very mineral. To decode those clues, we just need the right set of rules.
Section 1. Secrets of the Quartz. Now, to write the code, we first need to understand the physical mystery hidden inside this rock. And to solve it, we look at a process called trapped electron accumulation. Basically, you can think of this like a microscopic, totally invisible hourglass. Over time, as this quartz crystal just sits there in the Earth, it gets exposed to natural background radiation. And this exposure actually causes tiny electrons to get trapped right inside the crystal's microscopic flaws. So the longer the quartz sits there, the more electrons gather and just get stuck. It is quite literally a microscopic ticking clock. Every single trapped electron is like a tiny grain of sand falling to the bottom of our invisible hourglass, meticulously keeping track of the passage of time. But here's the thing. Crystals aren't perfect traps. You know, they don't catch absolutely every single electron that zips by. They have an efficiency rate. Let's say this particular piece of quartz has an efficiency of 5%. And this brilliantly illustrates how we bridge the physical world with the digital. We take the messy, super complex physical reality of the crystal's efficiency, and we transform it into a beautifully simple digital counterpart in our code. Crystal_efficiency equals 0.05. Boom! We've literally taken a complex geological reality and turned it into a clean, precise mathematical constant that our Python script can easily understand.
Section 2. The trapped electron clock.
All right, so now that we've got our physical parameters, the trapped electrons and the crystal's efficiency, we need a way to actually crunch the numbers and calculate the time that's passed. And here is the exact Python function from the source code used to do just that. Notice our parameters here. We're telling the simulation to look at two absolutely crucial pieces of evidence: the total amount of trapped electrons we found and that defaulted 5% crystal efficiency rate. This right here brings us to the absolute heart of our digital detective story. It's perfectly mapping our real-world geological findings directly to our mathematical model. And the really crucial point is right here in the source code's own documentation. The code literally tells us its purpose in a simple text string right beneath the function definition. It simulates the aging of a mineral based on trapped electron accumulation. This one simple line of text anchors the entire purpose of our simulation. It's just a great reminder that code isn't just, cold math for a computer. It's a narrative. It's a specific set of instructions written by human beings to solve a very specific human mystery, which in this case is figuring out exactly how old our mineral really is.
Section 3. Running the digital time machine. Get ready, because as we step into our virtual laboratory, which thankfully requires absolutely zero safety goggles, we are about to get to the good stuff. We fire up our completely virtual scanner, we scan our ancient quartz sample, and we get a hit. Now, what's really interesting about this slide is that our virtual scanner detected exactly 450,000 trapped electrons inside this one single piece of quartz. 450,000! I mean, that is a massive amount of invisible sand sitting at the bottom of our microscopic hourglass. It tells us, without a shadow of a doubt, that this sample has been sitting around for a very, very long time. But how exactly does our code handle that massive physical discovery? Honestly, it does it with incredible elegance. It simply states sample_measurement equals 450,000. That's literally it. That massive, awe-inspiring physical measurement of almost 500,000 microscopic events stretching over thousands of years, it just simply becomes a single clean variable in our Python script. We have effectively captured centuries of history and packed it right into a neat little digital box labeled sample measurement.
So let's look at the full action sequence of our simulation as an active procedure, really tying everything we've learned together. First up, we ran our virtual scanner. Second, we counted those 450,000 trapped electrons. Third, we applied our known 5% crystal efficiency. And finally, step 4, we triggered the final function call in our code, passing in our sample measurement. This is the exact moment our digital time machine actually powers on. We hand our massive variable over to the function, and it begins calculating the years based on the exact rules we set up. It's a completely satisfying logical sequence, and it's the precise framework that allows modern archaeologists to scale up their discoveries without, destroying rare physical samples in the process. But wait, there is a bit of a plot twist hidden at the very top of our source code file. Before the function was even defined, before the efficiency was ever set, the very first line of the script reads, import random. The code intentionally introduces a module specifically designed to generate randomness. But why? Well, because the physical world just isn't perfectly clean or mathematically rigid. Radiation exposure isn't perfectly uniform. Flaws in the crystal vary from piece to piece. By importing random, the code introduces a really crucial element of unpredictability into the simulation, which makes our digital model behave way more like the messy, unpredictable natural world.
Which leaves us with a truly fascinating paradox to think about. We've built this incredibly precise digital tool to uncover history. But if accurately aging a mineral requires us to intentionally simulate randomness and unpredictability within our code, how predictable is the past really? It kind of forces us to ponder the limits of our digital detective tools, doesn't it? Are we perfectly uncovering history, or are we simply running the most highly educated randomized guess possible? Thank you so much for joining me on this explainer. I really hope this changes the way you think about both ancient history and the code we use to understand it. Keep learning, and I'll catch you next time.